Okay, hello everyone. Sorry I was late in the class because I had a doctor appointment which I got after waiting for 2 months and didn't want to cancel it. That's why the class was cancelled, sorry. The class was cancelled but I still want to make use of the time and I would like to record the lecture and upload it so that you guys can watch it on your own so that it can be helpful for our class on Thursday. So I would request you to watch the video. And then if you still have questions, we can discuss them in the Thursday class. So coming to the lecture of today, the paper which we are covering in this week is side channel security of superscalar CPUs, which was oh, it's not DAC 2018. Okay, I will correct this mistake. It was published in Journal of Cryptographic Engineering in 2018. Uh, Okay. So what is the motivation of the problem, or what is like, why they wanted to work on the problem which they have addressed in this paper? So let's first talk about the people problem. So if you have checked those guidelines which I shared with you about reading a paper, in that paper they are advised to first identify the people problem, then technical problem, and then to the problem statement. So all these three things constitute the motivation of the paper. So the people problem which is addressed in this paper is that it is difficult to analyze vulnerabilities of a device to side channels. So for example, if you have any new microprocessor or microcontroller, any kind of device released, so it will be difficult for you to analyze what are the potential or hidden vulnerabilities of this device or this architecture for the side channels. So even not only that, even if let's say you have developed a software library uh, which is resilient to side channel vulnerabilities of a particular platform. So let's say the knowledge about the platform is known, the architecture of the platform is known, and considering that architecture, you develop a software a library or a program which is resilient to the side channels of that particular platform. But now, if you simply port your software to a different architecture, then you cannot guarantee that it will still be resilient to the side channel vulnerabilities of the new platform. So, which basically means that when you port your application or the program, the guarantees for protection against side channels are lost. So this is like what problem the people are facing. One, difficulty to analyze the vulnerabilities of side channel vulnerabilities of a new device. Second, even if you have developed a software that is resilient to the side channel vulnerabilities of a particular platform, the same software will not work on a new platform. So why people are faced, what is the like technical interpretation or technical understanding of these problems? So the issue is that software countermeasures that are developed, for example, a side channel resilient library that are developed for a particular platform, they do not work on a new platform because they do not consider the microarchitectural features of the new CPU or the new platform, and as a result, the effectiveness of that software those software countermeasures are not valid anymore. So that is the technical reason behind non-portability of side channel resilient softwares from one platform to the other platform, because the new platform has its own microarchitectural features, its own sources of information leakage, which are not covered by those software protections. So the research problem which is addressed in this paper is to analyze how microarchitectural features of a CPU, which can vary across devices, play a role in pinpointing the sources of information leakage when running software primitives. So how we can analyze a microarchitectural feature with the target of pinpointing the sources of information leakage, so that when we run the software program on it, we don't leak the information. So if we know which components of the CPU are leaking the information, so we then take them into consideration while we are developing our software, and we can develop our software in a way which will not trigger the information leakage from that CPU. So this is like the motivation or the target of the paper. But then what is the key idea? How they want to address that problem? So for that, they are using two approaches. One, they are using the performance measurement, for example, the measurement of clocks per instruction, and then use that measurement to infer the details about the microarchitectural features of a particular CPU, disclosed CPU. So just by measuring the performance and using a particular performance metric, they are going to use those measurements as a tool to infer the details about the microarchitecture features of that particular CPU. And second, that they want to use the power analysis to pinpoint the source of leakage information in that CPU, in a particular CPU. So in this paper, they are using ARM Cortex-7 as an example of a superscalar CPU, but the idea they have proposed is general in the sense that you can use the same approach, for example, measuring the CPI, clocks per instruction, to infer the microarchitectural details of other CPUs. Or you can use the power analysis to pinpoint the source of leakage information for other CPUs as well. So the idea is general, but they use the ARM Cortex-7 only as a case study. Okay, before we move forward, I think maybe some of you are not familiar with what is CPI or clocks per instruction. So actually, in computer architecture, when you want to measure the performance of a particular platform, or let's say a particular CPU, so you can use different matrices, and one of them is uh, clocks per instruction. So as it is clear from the name, it tells us that on average, how many clocks are consumed in executing a single instruction. So let's say if we have an add instruction, and it is completed in one cycle, then we say that CPI of the add instruction is one cycle. Clocks per instruction is one cycle. And let's say we have multiply instruction, and one multiply instruction is completed in 4 cycles. It takes 4 cycles. So then we will say that it does clock per instruction for multiply instruction is our multiplier is 4 cycles. But keep in mind that there are two different things, are two different concepts which we need to think of, or which we need to be careful about. First is the latency of an instruction. So latency of an instruction is like as clear like how long it takes to complete one instruction. And the other is the throughput. So throughput is, you can define the throughput in various different ways. So for example, if we have a pipeline processor, remember I gave you an example, very simple example of how pipelining works by giving you an example of washer and a dryer, right? So let's go back to the same example. So let's say if you want to process one bucket of dirty clothes, and washing take 10 cycles and drying also takes 10 cycles. So what is the latency of a single bucket to be processed? It is 20 cycles, because 10 cycles for the washing, 10 cycles for the dryer. However, let's say that let's say I further break it down, down our example of the pipeline. Like now I divide my washer also into 2 stages. So washing stage 1, washing stage 2, and also the drying stage 1 and drying stage 2. So let's say now each stage also takes five time units or 5 minutes, let's say. So still the total latency of washing a single bucket or processing a single bucket will be 10 time units. However, if now let's say if I process more than one bucket, so first bucket will be processed after 20 time units, but the second bucket will come out of the last dryer or dryer stage 2 5 seconds after the first bucket. So once the first bucket is processed, after that, after every 5 time units, I will be having one bucket ready on the output. So here the latency of a single bucket is 20 time units, but the throughput is we are having one bucket every 5 seconds. Okay, so it's mean that one bucket is processed in every 5 seconds. So if I simply reverse or flip the measurement or flip the units, so it means that it takes 5 time units to process every bucket, right? So 5 time units to process each bucket in a pipelined washing dryer system with 4 stages. So if now I take the same example and apply it in the domain of computer architecture. So now if let's say you have instructions and you have a pipeline to process those instructions, and first instruction gets completed in 20 time units. And after that, after every 5 time units, I have one instruction completed. So it's mean that five cycles are consumed for one instruction. So CPI in this case will be 5 cycles per instruction in this particular example. So I think now after explaining this, it is clear to you what is meant by CPI. So CPI is how many clocks are consumed in processing or in executing one instruction, clocks per instruction. So in this paper, as I said, they are using clock per instruction as a performance measurement and then leveraging it to determine or to infer the microarchitecture details of a particular CPU. How, we will talk about it later. But here, I just wanted to explain what the CPI is and what is the main idea of the paper. And the second thing is like they are using the power analysis to pinpoint the source of leakage information in a CPU. How, we will discuss it later, maybe on Thursday. So why is this idea supposed to work? With this idea, by this idea, I mean that why we suppose that we can use the CPI or we can use the power analysis to pinpoint the sources of leakage information. Because the power consumption model of a computation, so any computation which you are performing, when you compute something, it results in power consumption. And the power consumption done as a result of computation, it is expected to be unaware of the hardware details. So which means basically that we can apply this approach of power analysis on any platform, any CPU, irrespective of the differences in their microarchitecture details. So, but what we can do is that by measuring the power consumption of a CPU when we run different benchmarks, we can perform the differential power analysis, and this can reveal information to us about the type of the instruction executed and data operated on by these instructions. What are the details of the solution or how it works? Again, we will talk about it later, but here what we want to just focus is that since we can use this approach on any CPU, like for any CPU, what you can do is like in this example, in this paper, they have used ARM Cortex-7. But let's say you have a Skylake processor from Intel. So you can again use the same approach where what you do is that you run your program or your benchmark on the Intel Skylake processor. Then you measure the power consumption of that CPU. And then you compare your measurement against already known patterns of power consumption for different type of instructions. And then by comparing, you can these two patterns, one which you have measured for Intel Skylake and one which you have already in your database, like for every kind of instruction and the data processing, you can do the matching and then you can find out, okay, the program running on this CPU on Intel Skylake, what kind of instruction is it executing, or what kind of data it is operating on. So having said this like after discussing the motivation and main idea and why we suppose or why we think that this idea is going to work, or it is general and can be applied on other CPUs or other architectures. Now let's first cover some of the background or some of the terminology which is used in this paper and which will be helpful for you to understand the main body of the paper. So first, what is a superscalar CPU? Superscalar CPU is one that can issue multiple instructions for execution in a single clock cycle. So basically, it is a CPU in like in a scalar CPU. So things are known by their opposite. So let me first talk about a scalar CPU. Scalar CPU is one that can execute only one instruction in a cycle, or which can issue, not, let's say not execute, but which can fetch, decode, and issue only one instruction in a cycle. It is still pipelined. There are multiple instructions, but in different stages of the pipeline. However, in a given stage of the pipeline, only one particular instruction is being processed in a scalar CPU. However, this is not the case in superscalar CPU. In superscalar CPU, we can have more than one instructions in the same stage of a CPU. For example, we can have two instructions in the fetch stage, two instructions in the decode stage, two instructions in the issue stage, two instructions in the execute, memory, write back stage, and so on. So if it is a superscalar CPU with two issue, we will have two instructions in each stage, ideally, generally. But if it is four issue, then we will have four different instructions in each stage of the CPU, which basically mean that the processor will be able to execute four different instructions at the same time. Okay. So here is a logical figure or diagram of the ARM Cortex A7 microprocessor, which is a superscalar CPU. Again, when I say that it is the logical diagram, they have not shown that how two different instructions can be in the fetch stage at the same time. So let me get an annotate. Let me do the annotation. I don't know how to do it. Let me draw. Okay, I can do. So here in the fetch stage, they have not shown that how two different instructions can be in this stage at a given time. But they reveal that, they announce that it is a, dual fetch or dual issue processor. So similarly, there will be two instructions in the decode stage, there will be two instructions in the issue stage, and so on. And then after the issue, they have multiple functional units, like they have an ALU, arithmetic logic unit, floating point unit, FPU, and they have a load store unit. So now after that, the instruction will be directed after the issue stage, either to ALU, depending upon what kind of operation you need to perform. The instruction need to perform, it will be either directed to ALU, FPU, or load store unit. And now each block in ALU actually here indicates that ALU itself is pipelined, which basically means that it is a multi-stage ALU. It is not a single stage or one big unit. Similarly, floating point unit is also pipelined, and load store unit is also pipelined. And after that, you have the write back stage. So you have five stages: fetch, decode, issue, execute, which has multiple functional units, and then the write back stage. Now let me go back to the yeah. Uh, okay. Uh, let me check if I can erase it. Yeah. Okay, so now you know what is the superscalar CPU, and the superscalar CPUs, they are pipelined, and they have different stages in the pipeline. As I have shown you in the figure, like you have fetch stage. So in fetch stage, what you are doing, you are fetching the instruction as explained in the previous lecture. You are fetching the instruction from the memory. But if it is, let's say, dual issue superscalar CPU, at a time it will fetch two instructions, two consecutive instructions of the program from the memory, and then there will be decode. So now the two instructions at the same time, they will be decoded, and decoding mean that we will uh, unpack them to find out what kind of instructions are they. Are to add instructions or to multiply instruction? One is add, one is multiply. And then after that, we also need to find out that, let's say, if it is an add, they are add instruction, then what kind of operands they need. Where are their operands located? Are their operands located like source operands in register, let's say R1 and R2, or R10 and all 11? And then after, we not only need to know where are their source operands, we also need to know where to put their results back. Are we going to put the result back after addition into another register? Let's say and if another register, which register, let's say register 7 or register 8. And let's say if not in register, then if in memory, then in what location in the memory, so what address of the memory. So all these things happen in the decode stage. So after fetching, decoding, you have the next stage of issue. So the job of issue stage is in a superscalar CPU that in the previous stage you have, let's say, decoded 2 instructions. Now you need to issue them. So issue stage decide that whether these instructions are ready to be executed or not. And how it finds out that whether a given instruction is ready for the execution or not, by looking at basically 2 things. First, whether a given instruction, let's say a current instruction, has any dependency on a previous instruction. So if it has dependency, then it is not ready for execution, because it can be executed only after the previous instruction has been executed and its result is then ready. Only then the next instruction can be executed, because the next instruction has a dependency on the previous. So if a current instruction has a decoded instruction has a dependency on a previous instruction which is not yet completed, then it is not ready for execution. So it will not be issued to the execute stage. So issue stage not only then looks on the dependencies, even if the dependencies are met, there are no dependencies or all the dependencies are met, still then it will look at another thing. The functional unit which is needed by the decoded instruction, are those functional units available or not? Let's say you have an add instruction and it has no dependencies on a previous instruction. So it is from the dependency point of view, it is ready for the execution, but it needs the functional unit of addition, ALU, to be executed. But right now the ALU is occupied by another instruction in the next stage of the pipeline. So the ALU is not available. So then issue stage will not issue this add instruction for execution in the next cycle. It will hold it until the ALU becomes available for the execution of this current instruction. And since I'm just recording the video, I cannot take your questions, but if you have any questions, please send them to me by sending messages on the Canvas, or you can also ask them in our Thursday lectures. But uh, I will encourage you to send me on the Canvas, so that we can save the time, more time for the Thursday, and we can discuss more material. Okay, so Cortex AM, the paper mentions that ARM Cortex A7 is a superscalar dual issue processor, but it is a partial dual issue CPU. Now, what is meant by uh, meant by partial dual issue? So the partial dual issue basically mean that even when instructions are independent, when 2 instructions don't have dependency on each other, uh, in terms of like read after write hazard, for example. I will explain what is that later on. Still, some instructions cannot be issued both of them at the same time. Why they cannot be issued both of them at the same time? Because let me give you an example. Because, for example, let's say you have 2 add instructions and both of them are independent. Let's say first add instructions reads data from register R1, R2 and puts the result in R3. And the second add instruction reads the value from register R4, R5, perform the addition and put the result in register R6. So now there is no dependency between these two when you look at the assembly language of these instruction. However, the issue is that the register file, which is located at the decode stage, and which is needed basically so that you can read the data from the register file. You need to read the data for 4 operands now. R2, R1, R2 for first add instruction, and R4 and R5 for second add instruction. So which basically mean you need 4 read ports, right? But the issue is that the Cortex AM Cortex A7 processor has only 3 read ports, which basically mean you can read only 3 registers at a time, not 4 registers at a time. So if you have 2 add instructions, and each one of them are reading from 2 registers, so you cannot decode them at the same time. As a result, even these two instructions, when you look at their assembly language, they don't have any dependency because of the structural hazard. So this kind of hazard is known as structural hazard because is this the problem or the hazard is stemming from the nature of the or structure of your pipeline, which is basically register file in this case. So because of the structural hazard, these two instructions cannot be issued at the same time. However, however, if you have an add instruction which reads from two operands and then a second add instruction which reads one operand from the register file and the other operand is immediate number. So let me give you an example. Let's say the first add instruction gets the operand from register R1 and R2, adds them and put the result in R3. And the second add instruction, it gets one operand from register R4, but the second operand is the immediate number, which is itself packed inside the instruction code. And let's say that immediate number is 10. So you are saying just add R4 and with the immediate number 10, whatever the content of R4 is, add 10 to it and put the result in R6. Now, in this case, there is no structural hazard because these two instructions collectively need to read three registers, R1, R2, and R4. So our register file, it satisfies the requirement because it has three read ports. So in first case, two instructions cannot be issued at the same time. Here, two instructions can be issued at the same time. So that's why they are naming it as partial dual issue, because sometime you can issue the two instructions at the same time, but depending upon the instructions, and sometime you cannot. Okay. Now, another thing which is mentioned in the paper is ISA. Now, what is ISA? ISA stands for instruction set architecture, and basically what it does is that it defines the set of the instructions a processor can execute. So for example, you can execute the add instruction. Let me check if I can write. I think I can write. So for example, you can say, so it defines the set of all the instructions a processor is supposed to execute. So, and for each of those instructions, it specifies, the ISA specifies the format, addressing mode, and operation of each instruction. For example, let's say I have first instruction. I say add, and then I say R, R3, R1, R2. So here I am in this instruction, the format is that the first the R1 and R2 will be the source operands and R3 will be the destination. So it will be like whenever you, let's say I'm following a particular ISA. So let's say then everyone will understand from this that yes, R3 is the destination operand and R1, R2 are the source operand. There will be no confusion and no one will interpret it like, oh, R2 is the destination operand and R1 and R3 are the source operands. No, the format is fixed and specified. One thing. Second, this instruction is also telling you that what operation to do, which is basically the add operation. And third, this same add instruction can have different addressing mode. In this example, I mentioned only one addressing mode, which is a register addressing mode. For example, I can do the add operation again, but using a different addressing mode. Let me give you an example. Add R3, R1, and then I say R2. So here what I'm saying is that first R2 here, yes, R2 is the source, the value before the first comma R3 is the destination, R1 is the source, and whatever is inside R2 or after the last comma on the right side is also a source. But what is the difference? The difference is I'm saying use the value which is in the R2 not for the addition but as an address. So whatever is in R2 is a memory address. Go to that memory address, read the data from there, and then read the data from R1. Now add these two operands, one from the R1 and one from which you read from the memory, add them together and put the value or the result in R3 register. So this is, I'm specifying a different addressing mode. I'm still doing the addition. The format is specified and addressing mode is also specified. So in ISA, you will have a complete set of the instruction which is supposed to be executed by a processor which implements that ISA. So ISA is just a how to say a template, but then how you implement it on a processor is a different thing. And the implementation and the ISA, and the implementation of ISA and the specification of ISA, they are two different things and independent of each other. They are not like, how to say, hardwired or connected to each other. You can have one single ISA and many different implementation of many different architectures which implement the same ISA in different ways. Okay, now let me rub this first. Okay, so in previous slide, I said that it is possible that you have a single ISA, but by many different architectural implementations of the same ISA. So, which is known as microarchitecture. So what is microarchitecture? It is the internal design and organization of CPU components, and it gives the detail how execution of ISA is implemented. So it is possible. I'm not going to go in the, I'm not going into the detail of a particular implementation of ISA, but here I can show you different examples. For example, x86 is a ISA which is used by Intel, and then Intel has many various implementation of the same ISA on different processors. For example, 8086, 286, 386. These are all different CPUs, but all of them implement the same set of instructions, but in different way. Maybe one of them is sports 16-bit operation, another sports 32-bit operation, another operates 64-bit operations, but all of them operate or use the same execute the same set of instructions. Okay. Now, in the paper, another thing which is mentioned is the pipeline buffer. What is pipeline buffer? Let me first draw and then I can explain. So what happens is that, remember I showed you the figure where you have 5-stage pipeline: fetch, decode, issue, execute, and write back. So let's say I'm just writing, let's say I'm writing fetch, F for fetch. Yeah. And then decode, D for decode, and I for issue, and execute our memory is our 4th stage, and write back is our 5th stage, where we write data back into the memory or back into the register file. Okay. So now what happened is like our if it is a pipeline, processor, then we have different instructions in different stages of the pipeline. So now let me also write to show it what I mean. So let's say we have instruction 1 here. So our pipeline is progressing from left to right. We have I2 in execution and executor memory stage. We have I3 in issue stage. We have I4 in decode stage. And we have I5 in instruction 5 in fetch stage. So basically what we are saying is that our pipeline is full, right? So now if, let's say, if our instruction at a given time, our I2 instruction is in execute and memory stage, and our I1 instruction is in write back stage. So we want to decouple them in the sense that the signals or the data flowing from one stage to the next stage should not affect the execution of the stage in the execution of the instruction in the following stage until the clock makes a progress or the clock the next clock edge arrives. So basically what I mean is that our I1 is in the write back stage, so it is doing its job. So whatever we do in the write back at the current time, I1 is in the write back stage, and our I2 is in execute or memory stage. But there are connections, there are data and the data and control signal connections between each stage. So like for example, execute a memory stage to write back stage. Let me also draw them, right? Uh, so let's say we have signals here flowing in this direction, okay? But if we allow these signals to affect the execution of I1 in write back stage at any time, so it will corrupt our design. So what we need to do is that we need to put buffers in between. So yeah, so we need to buffers in between. So what we do is that we put a buffer here. So what is the job of the buffer? So job of the buffer is that yes, the signal is there is a value on the input line and there is a value on the output line. However, the value on the input line is not reflected on the output, the new value basically. The input is not reflected on the output until we have a clock cycle. Sorry, let me also draw this again. Until we have a clock cycle arriving here. So if the clock cycle is arrived, then whatever signals or the value of the signals and data we have in the E and M stage, it will progress into the write back stage. Now, same what we have is that we have buffers between every two stages of the pipeline. Yeah, let me draw it again. So we have a buffer here, we have a buffer here, we have a buffer here. Okay. And all of them are connected with the same clock. So all of them are connected with the same clock. So as a result, now what happened is that if the clock doesn't arrive, there is no positive, let's say no positive edge of the clock, the signals and the data in the fetch stage, they will not affect, they will not propagate into the next stage, uh, and they will not affect the decoding of the instruction I4. And similarly, the signal and the data of the decode stage, it will not propagate into the next stage, issue stage, and as a result, they will not affect the issue logic which is being applied on instruction I3. And similarly, the control and data signals of issue stage will not propagate into the ERM stage, and so on. Okay, so I guess now you get the idea of what the pipeline buffer is and why is it used for. So now let me read my notes now. So what is a pipeline buffer? It stores the signals and the data which cross when it crossing the boundary of the two stages. So it actually doesn't allow the signals and the data to be propagated to the next stage until and unless we get a clock signal. So new information is stored coming from stage I on every clock cycle, which then triggers the computation operation in stage I plus one. Basically, what I mean is that uh, if you, let's say you have an input here, so this input will not propagate to the next stage until the clock cycle arrives. So if the clock cycle arrives, then this will appear into the next stage on the output of the buffer, and as a result, the decoding based on this new input will start. Okay. So I think now it is clear what I mean by pipeline buffer, or what is meant by a pipeline buffer. Uh, so definitely the pipeline buffers are important, but they have their drawbacks because they have power consumption. And actually, ideally, the thing is like larger, not let's not say the larger. The deeper the pipeline you have, the more performance improvements you can get. But this is ideal in ideal case. But the buffers you need to put in between every two stage, they have their overhead. They it takes some time from input to go through the buffer and then appear on the output, one thing. So which means that it increases the latency. Second, uh, every buffer has its own power consumption. So more buffers you have, more power consumption you have, and which makes your which can increase the power consumption of the chip as a whole. And yeah, and maybe the buffers can also become a source of information leakage, as we will see in this chapter. So more buffers you have, more sources of information leakage you can have potentially. Okay. Now, what is read after write hazard? So I mentioned this hazard earlier, but now I'm going to give you a detailed description of what read after write hazard is. Actually, what happened is that whenever you are running a program, what are you doing? You are executing multiple instructions, and it is possible that the instructions which make the sequence of the instruction which makes the program. So there are dependencies between those instructions. So there are basically different kind of dependencies. I am not going to describe other kind of dependencies, like there is write after write dependency, write after read dependency, read after write dependency. But other dependency like write after write and write after read, they are not real dependencies because they can be resolved. For example, by using the techniques like register naming, you can go and Google on your own what are these dependencies, write after write and write after read, and how register renaming can be used to resolve these dependencies. However, read after write dependency is a real dependency and it cannot be resolved. Now, let me give you an example of read after write dependency. Let's say you have two instructions. First instruction is add R3, R1, R2. So you are saying that add the value of R1 and R2 register and put it in the result in the R3. And you have another instruction in your program. So these are two consecutive instructions. So next instruction is multiply, which says multiply R5, R4, R3. So here what you are doing in the second instruction is multiply the value of the R3 register with the value of the R4 register and put the result in R5. Now there is a dependency. Uh, there is a dependency because of the register R3. So R3 is the output register for add, but it is the input register for multiply instruction, which basically mean that we cannot execute the multiply instruction until the result of the add operation is ready. So if the result of the add operation is ready, after that, we can use that result and only then we can execute the multiply instruction. So since in multiply instruction, we are reading the register R3, but in the add instruction, we are writing the register R3. So that's why it is called read after write dependency, basically, which means that we can read the register R3 in multiplication instruction only after the same register has been written by add instruction. So this is known as read after write or raw hazard. So this is data dependency between two instruction, and it is the only real dependency that cannot be resolved. So we need to respect that dependency. And I have shown you an example. Okay, now let me rub all this thing again. Okay, so now the issue is that question is how raw hazard hinders dual issue of two consecutive instructions. Uh, Explain on board. Actually, I have explained you already, or maybe I can like try to highlight it again. Now, let me give you again the same example. Let's say I have add uh, add R3, R1, R2, and I have multiply instruction which says R5, R4, and an immediate number. Okay, so IMM indicates the immediate operand, which is like part of the instruction itself. I don't need to read it from any register. So now there is no dependency between these two instructions, right? No raw dependency. Since there is no raw dependency, uh, we can issue them we can issue them at the same time. So basically, which means, like, let's say both of them were fetched at the same time, then both of them were decoded at the same time, and then both of them can be issued because there is no dependency between them. And if we assume that both header and multiplier are free, so then both of these instructions can be issued into the next stage for execution, right? Since they don't have the dependency and the functional units are available. Now, let's say I simply change the same. Let's say I simply change the same example. Oh, sorry. Yes. Now let's say I simply change the same. I didn't want to write. I just wanted to copy over, but I think I cannot. So let's say I simply modify these instructions. Now I have add R3, R1, R2, and I have multiply R5, R4, and R3. So this is actually the same example which I mentioned you earlier, which I mentioned to you earlier. So basically we have the raw dependency between add and multiply. Since now there is they both of them were fetched together, both of them are decoded together, both of them enter the issue stage at the same time, but then they are not issued for the execution in the issue stage. Why? Because yes, let's say adder and multiplier unit both are available, but there is dependency. So we cannot issue multiply and add instruction for execution at the same time. We must first issue the add instruction and for the execution, and when the result become available, then the issue stage will release the multiply instruction because it is the time when the dependency is resolved, because the data is available, right? So as a result, what we see is that when there is a raw hazard, it hinders the dual issue of two consecutive instructions. Okay. Now, what is a NOP instruction? So NOP instruction, actually, its NOP stands for no operation, and it's clear from its name that this instruction performs no operation. So then why it is there? Because sometimes we need to flush the pipeline. So what does it mean by flushing the pipeline, and why we need to do the flushing? So let me try to explain. So let me draw again our very simplistic pipeline. Let's say we have pipeline with, let's say we have a pipeline with 4 stages, right? And as I said, at any given time, we will have different instruction in different stages, right? Let's say I have instruction 4, I have instruction 4, instruction 3, instruction 2, and instruction 1. So they are like in different stages of the CPU, and our execution is progressing from left to right, right? Now, let's say something happens and we need to, when I say something happens, maybe I can explain it later. An example is, let's say you are doing branch prediction and you predicted that the branch will be taken, and so let's say you have a if else construct. And if the condition is true, execute block 1. If condition is false, execute block 2. And you predicted that the condition will be false, and you started executing the block 2. But later on, it turns out your prediction was false, and actually the branch was taken. So it means that whatever instructions you executed from the block B, you were not supposed to execute them, but you have executed them already, and they are occupying the different stages of the pipeline. So let's say those instructions from block B are the instructions I1, I2, I3, and I4. So we need to now flush them. We need to remove them from our pipeline. So now how can we free them? What we can do is that we can issue a NOP instruction. If we issue a NOP instruction, what will happen is that uh, if I issue an op instruction, so in next clock cycle, what will happen is that the knob will enter in this stage. So in next cycle, the knob will enter in this stage. And what will happen that I2 will be here, I3 will be here, I4 will be here, and here in the first stage I will have knob. In the next clock cycle, so let me indicate knob with a cross. So in the next clock cycle, I will have another knob. I will issue another knob, so it will enter in the first stage. First knob will move into the next stage, and I will have I 4 in this stage and I3 in this stage, right? And then I will keep issuing. So in next cycle, again, I will issue another knob. It will enter in the first stage, then the older two knobs will progress, and they will occupy the next two stages of the pipeline, and I4 will be in the final stage. And then in the final cycle, I will issue another knob, and which is like, and which will in the first stage, and the older three knobs, they will make progress, and then uh, the I4 will be flushed out from the stage. So now my pipeline is clean. It has no partially executed instruction, or it has no leftover from previous instructions which I fetched in and started execution as a result of my misprediction. Okay, so that's why sometimes we need NOP instruction to be issued and executed to flush our pipeline. And here what we see that if we have a 4-stage pipeline, then we need to issue 4 NOP instructions to completely flush the pipeline. Okay. Okay, now another thing which is mentioned is in the paper is a barrel shifter. Uh, so what is a barrel shifter and what problem it solves and how it works? So let me check the time. Yeah, okay, let me complete this thing and then we can stop, and remaining slides I can cover them on the Thursday with the new slides or with new material. Okay. So now let me delete all of this. Okay. So what is a barrel shifter? So before talking about the barrel shifter, let's talk about what is a shift operation and how a shift operation happens in a register. So again, yeah, I think I can draw the like freehand drawing. So let's say you have a register, and let's say you have a 4-bit register. And let's say the value you have uh, in this register, I'm just indicating by writing them as B0, B1, whatever the value is, I don't know. I'm just putting the symbols. Okay. Uh, Let me not put the symbol because it will make difficult for me to write. So I can write the values instead of symbols. So let's say this register has values 0, 1, 1, 0, right? And I am assuming that this is our least significant bit. And here we have most significant bit. Okay. So now let's say I want to perform the shift operation or rotate operation. Let's say I want to do the let's say not rotate. Let's say I want to do the shift operation. You can go and check what is the difference between shift and rotate operation. I'm not going into that detail, but I'm focusing, I'm using shift operation as a use case to explain how what is shifting and how barrel shifter works. But same thing, whatever advantage we get from the barrel shifter, we can also use the barrel shifter for optimized rotate operation as well. Okay. So now let's say I want to do the left shift operation. So left shift operation mean by 1, which basically mean that I want to rotate the content of this register to left by 1. So after left shift operation by 1, what will be the new input? Or what will be the new content, not input? What will be the new content of the same register? Let me draw it again to indicate the new content. So when I shift left, 0 will go, 0 will go out. So it will be discarded. One will move, every bit will move by one position. So every bit will move by one position. So as a result, the most significant bit will be discarded. So I will get one here, one here, one here, sorry, 0 here, and the least significant bit will be filled with 0. Okay. Now there is arithmetic shift and there is logical shift. Logical shift operation and arithmetic shift operation. What I'm doing is called logical shift operation. Okay. You can go and check what is arithmetic shift operation if you don't know. But here is what we have, the new content of the same register. Okay. But the issue is, like, if I want to do, if now here I shifted all the data only by one time, right? So it will now take me one cycle to shift the data by one clock cycle, right? Now let's say if I want to shift by 2 clock cycles. So I want to perform the left shift operation on the same register, by 2. I want to do the left shift by 2. Then what will happen in first clock cycle? I will get this output, and then in the second clock cycle, I will uh, get a different output. Not output again, a different content. The content will change to in the second cycle. This one will be thrown out, and so everything else will be moved by one on the left, by one position, and the least significant bit will be filled with 0, right? So this is the snapshot in the second clock cycle, right? But it takes longer. Now let's assume that I have a 64-bit register and I want to left shift its content 8 times. So it will take me 8 cycles, or 16 times. It will take me 16 cycles. Or if I want to clean or reset the register by 0, all zeros, then I want to left shift everything, left shift 16 times. So it will 64 times. So it will take me 64 cycles, which is very expensive. So it will take longer time, right? So how can now I reduce the latency? So for example, let's say if I want to shift the content 2 times on the left side, how can I do it in a single cycle? Can I do it in single cycle? Yes, I can do it in a single cycle by using the barrel shifter. By using the barrel shifter. So this is the problem, which is the problem barrel shifter solves is that it can perform uh, multiple left shift or right shift in a single cycles. Unlike the traditional case where we need multiple cycle to perform multiple left shift or right shift operations. Okay. Uh, and how it works, let me explain this and then I will stop. Yeah, let me rub all this. So before I explain how barrel shifter work, okay, you cannot answer my question, but I'm assuming that many of you don't know what is a multiplexer and how it works, right? Uh, hmm. So let me first explain the multiplexer. So this is the symbol for the multiplexer. And what it does is let me consider let me ex, cons, what the job of the multiplexer is that it has multiple inputs, multiple data inputs, and then it has the control signals, and then based on the value of the control signals, it allows only one of those multi inputs to be reflected on the output. Okay, so now let's say if I have a 4x1 multiplexer, which basically mean it has 4 inputs and 4 outputs. So let's say these are 4 inputs. Okay, I'm not drawing arrows. You can assume that these are the inputs and this is the output. Okay. So four inputs and one output, but then multiplexer selects among four inputs. So if you want to select among four inputs, you also need control signals. So how many control signals you need to select among four input? Two control signals or two lines. I am indicating by writing it two. So it is a two-line bus. So why we need two? Because 2 raised to power, if you have two bits, how many combinations you can make? You can make four combinations. I'm not writing them, I'm just saying them. 0, 0, 0, 1, 1, 0, 1, 1, right? 0, 0 is binary of 0, 0, 1 is binary of 1, 1, 0 is binary of 2, and 1, 1 is binary of 3. So what we can say is like, okay, let me also write here. So let's say this is uh, data input 1 or data input 0. This is data input 1. This is data input 2. And this is data input 3. Okay. So what you do is like you indicate when you are like representing a multiplexer, you indicate like uh, here you indicate 0, 0. Or only 0 maybe in decimal. And here you indicate 1, here you indicate 2, here you indicate 3, which basically mean that when the 2-bit value of the control signal is 0 in decimal, then allow data input 0 to be reflected on the output. So it connects this input to the output. When the 2-bit value of control signal is 1, then this input is connected to the output. And when the 2-bit control value is 2, then data input 2 is connected to the output. And when value of the control signal is 3, then data input 3 is connected to the output. So this is how multiplexer works. Okay. Now I think everyone is clear how multiplexer works. So now I'm going to show you how barrel shifter operates. I explained multiplexer because barrel shifter uses multiplexers. Now, again, I mean, I cannot go to more lower detail, but you can go how internally the multiplexers achieves uh, connecting multiple inputs at different time to the same output. You can go and check Google, or it is very basic knowledge in digital design. You can go and look. Okay. Okay. So now let's go back to our uh, example of 4-bit register. Okay. So what they do is like you can put a multiplexer here, let's say. So remember, before I explain that, in the traditional shift operation, this bit can get data only from its neighbor on the right? So we can transfer data only from in this direction. Every bit can get the data only from its immediate neighbor on the right? And it cannot get data from directly from any other bit. It can, if let's say this bit here wants to get data from this bit, it will take me how many cycle? 1, 2, and then 3. So in 3 cycle, the data of this bit will become available here in this location. So which mean it takes 3 cycles. Otherwise, I cannot get directly data from here to here, right? So barrel shifter makes it possible. How? Let me show you. Okay. So let's say you have a multiplexer. So what you do is that you connect the output of the multiplexer with the input of this bit location. So actually each bit is stored in a latch. So I'm not going into that direction, but let's say I will use the word bit location, okay? And the 4 inputs and the inputs of this multiplexer, they are coming from the output of these registers, output of these bit locations. Oh, sorry. And then you have another bit input, which you fix to 0. Okay. So now, and then you have control signals, right? And in this case, this is a two line bus. Control signals are 2-bit. Okay. So now depending upon the value of the control signal, I can put in this bit the value either from this location, or this location. How? If the value of the control signal is, let's say, let me put here 0, 1, 2, and 3. Sorry for the writing. So if the value of the control signal is 3, this bit location will be selected and inserted into most significant bit position. If the value of the control signal is 2, then this bit will be selected and inserted into the most significant bit position. And if the value of the control signal is 1, then this bit, least significant bit, will be selected and it will be moved into the most significant. And if it is 0, then 0 will be placed here, right? So now let's see how many cycles it takes me to transfer the least significant bit into the most significant bit position, single cycle. Because I can apply the control signal of equal to 1, and this will be gone through the multiplexer and placed in the most significant bit position. So now this is different from how we were traditionally doing. Traditionally, it needed me 3 cycles to move the least significant bit into the most significant bit of a 4-bit register. Now, in the same way, I can insert a mux here, a mux here, a mux here. So for example, the mux at this position here, it will have 4 inputs again. One of them will be 0, and the other 3 will be, one will be coming from this bit, most significant bit, another from this one, and another from this one. So in this way, I can control at any time that how many positions I want to shift in the register, and I can do that shifting irrespective of amount of the shifting, or like how many shift operations. I can shift them in the single cycle. So this is how barrel shifter works, and this is how it improves the performance. So definitely there is trade-off of everything. Now you have an extra hardware. You have 4 multiplexes, for example, only for this 4-bit register, which will take more space. And as a result, they will, since they are all of them are operating, all of them will be consuming power. So as a result, the total power consumption will also increase. But as I said, again, there is trade-off of every design. Okay, now let's stop here and I can discuss remaining in the next lecture. Thank you.